and this was the calculation of the primary surface area. So this was relatively small. Then we had the fin surface area, which was much larger, almost like 10 times. Like this is 35 and this is 331, so almost 10 times. Yes. Today is lecture 15. In lecture 14, we had gone up to approximately here. So the total area on the air side is the primary area plus the fin area. So that gives you this much, 336. And we have this kind of a triangular arrangement. And in this arrangement, we are also interested in finding what is the free flow area. So we are talking about the flow that will take place through this, correct? Just to remind you that we are talking about this sort of a situation. This arrangement is triangular, equilateral triangular pitch arrangement. And when we talk about free flow area, we're talking about this area which you are getting here between the tubes, that are already finned, the free space. We're talking about that area. We have already talked about primary area and fin area, but now we are talking about that free flow area. So for that one, this is the arrangement, and we had some discussion about this minimum free flow area when we were discussing this theory. So that was like this, okay? If you have already revised this part at home, then you will be able to recognize what this area is. Okay? So we have these tubes. Okay, we have these tubes, and this flow between tubes is what we are talking about. That is a free flow. And that's this thing. So here, this is the effect of the fins, right? If there were no fins, then the free flow area would have been like this. Again, what is L3 over PT? The first thing that when we are talking about geometry, we spent half an hour on geometry in the last class. So what is L3 over PT? The number of, it's a number. L3 over PT is a number. So this is a number of, number of tubes in the first row. Actually, it looks like a column, but we call it a first row. Okay, so that's L3 by PT, and then if there were no fins, then it would be just L3 over PT multiplied by this. But we have the effect of fins, and this is dE minus dO is some height, right, above the tube. The tube is, this is tube, which is like, this is DI, this thing is DI, and this thing is DO, but we also have the fin, which gives this much extra thing, right? And for the fin, we are saying that the diameter is DE. All right. Where do we use this? We'll use this in getting hydraulic diameter. This free flow area, this will give you a hydraulic diameter. Hydraulic diameter for the flow external to the tubes, right? Now we also calculate, the book has also calculated porosities. What is porosity? Porosity is this area divided by L1, L3. Okay. What is L1, L3? So you can just remember this one. Remember, we said that this is L1. So L1 is the depth dimension here. So we do L1, L2, and the height is L3. Okay. So the porosity is L1, L3. Okay. What is that area? That is this face area. So the flow is seeing this face area, but it's not seeing the entire area because it's blocked by tubes and fins. So there is a certain porosity. So that porosity is this. Now the hydraulic diameter I discussed in the last class is 4AC divided by kind of like a perimeter, which is AC divided by L2, right? I discussed again last class why this is L2 and not L1. And this is TH2. So we got AC to get the Reynolds number, and this is the Reynolds number calculation. All right, so this is m dot divided by AC is g, which is the mass velocity. What is the unit of this? Kg per meter squared second. Kg per meter squared second. So using that g and the hydraulic diameter and viscosity, we get a Reynolds number. Okay. And then we can, once we got the Reynolds number, maybe we can calculate J also. J is the Colburn factor. So that J is like this. And in the notation that the book is using, it kind of looks like this, but ultimately it's this one, which we talked about. So that J depends on Reynolds number. It also depends on the fin pitch, which is P subscript F. Okay, and there's a delta, which is fin thickness. Then there are also DE and DO. So once we have J, and we are writing 2 for this, the notation that we are writing 2, 2 for the flow outside the tubes. Okay. So this is the calculation of J, and once you have J, using this relation, we can also get the heat transfer coefficient. So J is Stanton number multiplied by Prandtl to the power 2 by 3. This is something which you must have seen in undergraduate. And the Stanton number will turn out to be H divided by GCP. Okay, or H divided by rho VCP. This is Stanton number. So you can in fact calculate H. H will depend on this J, but the J you have already calculated using this expression. Right, so we got H, we have got J. And what is next? So one thing that is still remaining is getting the friction factor. The friction factor is this, but we'll come to friction factor a little later. Before that, now we'll have to also tackle the fins. So these fins, as I mentioned in the last class, are circular, not rectangular fins. But what do we need with respect to the fins? We need the efficiency of a single fin, and that can be used to get the overall efficiency of the fin surface, isn't it? That's what we did for rectangular fins. Each fin has an efficiency, and if you have a fin surface, then the fin surface has an overall efficiency, which will depend on the individual fin efficiency, right? So this fin efficiency is the individual fin efficiency, but this looks very different because this is for a circular fin, which we didn't see previously. Now this has got things like I's and K's. So you will see I naught, K naught, I1, K1. What are these things? These are I and K. Mathematically, these are, anybody know? These are? No. Moment of inertia will not come here. I is moment of inertia, but it will not show up here because we are not doing mechanics. These are Bessel functions. Okay. So, like you studied Bessel functions in engineering mathematics, so these are Bessel functions. These show up because it's the circular geometry, right? And these are Bessel functions of different types. So this is I0 and there is also I1. Okay. And there is some M which you see, M we will to calculate M also. So the M is 2h by kt to the power half, the usual thing about M, isn't it? M is square root of hp over kc, so that is 2h by kt to the power half. So this is a familiar thing. Now, this is a calculation of M, and once you have that M, then you can also calculate this P, okay, C1, which goes here. So using all this, you can calculate efficiency of a single fin. So there has to be some table somewhere which you have to look up to get the Bessel function value, right? Better still, if you have a code which gives you these values, then it becomes easier for you. Right? Now that individual fin efficiency comes out to be 0.819. And using that, you can get an overall surface efficiency, which is eta O. Okay. Right, so we'll use these. Now let's also see water side Reynolds number and mass velocity. So what are the fluids? Like, this is an example problem, isn't it? So what are the fluids we were talking about? So this is hot wastewater. Like there is some process in some factory, so there is some water coming out which is heated, which is not being used. So they are thinking that, okay, cold air can be heated using the heat of that, using the internal energy of that wastewater. So that's the idea. So this is water side Reynolds number. So water is flowing where? In the tubes. Air is flowing outside. So this one is easy to understand. The first expression AC1. Then we have G1 and then V1 is the velocity in the tubes. So that's 1.273 meter per second. And the Reynolds number is calculated like this. So this is for tube flow, 7.718 10 to the power 4. We saw another Reynolds number. Okay. So that is 5841. Which was this Reynolds number? This was the Reynolds number on the air side. Okay. So the tube Reynolds number is much higher. What is 7.7 10 to the power 4? How big is this? So this is like 77,000. So this is what kind of Reynolds number? For tube flow, this should be turbulent, right? Okay, now the friction factor. Friction factor is given by, again, this correlation. So you have this sort of number for friction factor, and you have Nusselt number using that friction factor. This is again another correlation. We are talking about which side. This F1 is a friction factor for flow inside the tube, correct? How do you know? The simple way to know is that, okay, if you recognize the correlations, you will know. Otherwise, also, we are using subscript 1 for the tube side. So this is F1. So F1, you got this number. And Nusselt number 1 is, okay, in terms of friction factor. And this is the expression. And from Nusselt number, so you know the friction factor, you know the Reynolds number. And you can do this calculation. And once you have that, you can get the heat transfer coefficient. That turns out to be 8,473 watt per meter squared Kelvin. So is that a small number or a large number? What do you think? Just to get an idea of these sizes of these numbers, like, is it a big heat transfer that is happening, or is it a small? It's a big thing, right? When it's a high enough heat transfer coefficient. And this is the wall thermal resistance, RW. Okay. Ultimately, this is A1, and this is A1 is the number of tubes multiplied by the tube surface area, individual tube surface area. And then you have all these resistances. So this looks a little clumsy, but basically RO1 is nothing but RO1. Just disregard whatever is there within brackets. Brackets show, RO1 within brackets L1, L2, L3. They just show dependencies, but you know the dependence. So don't have to bother so much. So this is just 1 over H1 A1. That's a simple thing, right? Similarly, RO2 is 1 over H2A2, but modified by that efficiency factor, overall efficiency factor, right? So that is this one, overall efficiency. So we have RO1 and RO2, and we also have RW. So we can calculate UA, which turns out to be this much. Right. So what is it that we usually try to do from your experience of the Shell and tube heat exchanger? We try to go to epsilon NTU thing, right? So we try to go to effectiveness. Why? Because once you have effectiveness, effectiveness gives you something like flow rates and the temperature differences, right? So whatever temperature is not known can be calculated once you have got effectiveness, right? How do you get effectiveness? Using NTU, because effectiveness NTU relations are known. But that's okay. How do you get NTU? UA over C min. Okay, C min is a relatively easy thing. UA you have to know. UA you are getting like this. To get UA, we had to do so many things. We had to do correlations for friction factor, for heat transfer coefficient. Ultimately, once you get heat transfer coefficients, then you can do these calculations. You need both the heat transfer coefficients, no? Inside the tube, outside the tube. But we also have fins, so the overall efficiency of the fin surface is also important. That also shows up in the RO2 expression. Okay, so this is the overall picture. Now, in effectiveness NTU thing, as I said, yeah, you need a C minimum, you need a C maximum, so you get CR. So these things are relatively easy, so you can check this out because we know m dot and Cp, correct? Cp, we do not know fully one temperature we had to assume, remember? Isn't it? But we work with that estimate and then we get CR. We also have NTU because we just found out UA. And then we can calculate NTU to be 0.389. And then this is the expression for fluids in cross flow, unmixed cross flow. So that gives you effectiveness of the heat exchanger to be 0.287. And once you got the effectiveness of the heat exchanger using C min, you can calculate C min and T1i minus T2i. You can get the heat transfer Q. Right? You have this Q, and using all this, you can get this temperature T10. So what is T10? It's the water outlet temperature, right? Water outlet temperature. So water outlet temperature turns out to be 77. And the T2O turns out to be, T2O is the air outlet temperature. It turns out to be 30. What was the objective? Objective was to heat the air to 30 degrees Celsius. So this is what we were trying to do. We want the air to leave at 30 degrees Celsius. Air we already have, no? In that factory we have air, it's at a very low temperature, 5 degrees Celsius. Maybe the ambient temperature is quite low. So you get 30 degrees Celsius is what you want. And hot water is at 92 degrees Celsius, right? This is where we started. Actually, we should look at this figure. And basically, this is water outlet temperature. Okay. So the water outlet temperature is to be determined. This one is kind of known, but it has to be verified. I mean, you have assumed a few things, you have done some calculations. Ultimately, it should be 30. It should not be very different from 30. That is the object. So that's how we proceeded. Just keep this in mind that we will use effectiveness NTU method. So we need effectiveness. To get effectiveness, we need NTU as well as CR, C min by C max, correct? And to get NTU, we need UA. To get UA, we need H inside, H outside, as well as the efficiency of the fin surface, right? You put everything together in this framework, these problems are not very difficult to do, correct? So where were we? Yeah, so we satisfied all this. And now we should also calculate the pressure drop because pressure drop is limited. Uh, what were the values? 250 Pascal, right? 250 Pascal. And what was the other one? Anybody remember? 2 kilopascal. 250, 250 Pascal. Okay, 250 Pascal. Water side 3 kilopascal. Okay. Yeah, going back to the problem statement many times is sort of uh, tedious. So pressure drop on the air side. So the air side pressure drops comes from that Robinson-Briggs relation for friction factor. So we have something like this, and that helps you calculate this friction factor on the air side to be 0.019. And to get the pressure drop, there was another correlation. So that correlation was this one. And to calculate this, we need this friction factor F, we need the hydraulic diameter, then rho I, rho O. I suggest that you go through this yourself. I mean, there's no point me discussing how to calculate using a correlation. You can figure this out. And then to do all this, we need some density calculations also. Ultimately, we get delta P2 as 250 Pascal. So again, the values that he has chosen, the design that he has chosen, that seems to give you what is wanted in the problem, but that he must have done some iterations, and he's presenting the final results here. The pressure drop on the tube side is this much. This is much more familiar. Pressure drop on the tube side. On the tube side, there are no fins. So this is a simple geometry, straight circular tube, right? So this you know. And this pressure drop turns out to be again 3 kilopascal. So again, something which satisfied what we wanted to have. And that means these, he says that the initial guesses were these, but actually he'd worked with these numbers. Okay. So these are L1, L2, L3, and these conditions are met. And something about the heat transfer area and the volume calculation. The volume of this heat exchanger is L1, L2, L3, simple. But the total area is A1 plus A2, and beta is this much, 394.118 meters squared per meter cube. Why is beta important? Beta tells you something about how compact the heat exchanger is. So when it comes to heat exchangers, we said that area by volume thing is important. And if this is about 700 meters squared per meter cube, then it starts becoming a compact heat exchanger. If it's more than this, then it's a compact heat exchanger. Why do people say 700? It's kind of based on experience and somewhat arbitrary. I mean, why not 650 or 600? It's just an industry practice, that's all. So this is a bar graph sort of thing which you have seen before. So fin tube heat exchanger is like becomes, see, this compact heat exchanger is at about 700, as I was saying. Okay. And some fin tube heat exchangers are compact, some are not. Okay, so this one is actually not compact because it's only 394. Right. A few other calculations are also there as part of the problem. What is the power of the fan? What is the pumping power and all that? So that also you can check the calculations yourself. Right. So we have about 20 minutes. And in these 20 minutes, we'll like to look up the third heat exchanger that we are talking about. So we have done shell and tube heat exchanger, and we have also done pinned tube heat exchangers. So now we'll talk about plate fin heat exchangers. So this is a bit more complicated when it comes to geometry. So broadly, you see this, right? The geometry changes, isn't it? And if you can describe the geometry properly and do area calculations, then the rest of the process is similar, right? The shell and tube heat exchanger as well as the fin tube heat exchanger, it's basically the same sort of approach, right? Here also, the approach will be the same, but the geometry in this case turns out to be more difficult. So these are more compact heat exchangers. These are the most compact heat exchangers. So as I said, that surface area density of more than 700 meters squared per meter cubed. This has a name. We call it a beta. So this one more than 700 is compact heat exchangers, and the surface area is often increased with the help of fins. And there can be some. This is an example of a heat exchanger where surface area density can be quite high. So this can be a surface area density of 5,900 meters squared per meter cube. Just some example. Okay, where do we use these heat exchangers? These heat exchangers are used in power plants a lot, condenser and automotive systems, right? But how do they look like? They look like this. Okay. So this is a bit complicated. Now, what do we see here? You see these surfaces that look like so there are some plates. You can see some plates, and on the plates, you have this sort of thing. Right? Obviously, what I have drawn here is this sort of thing which is attached to a lower plate, correct? So this has finite thickness. So it's actually like this. This is on a plate. So the flow goes like this. Now, this is on one surface, but there is a similar arrangement on the lower one also. Okay, what I mean is, so let's say there is some gas, which we are calling it fluid 1, that will flow through this layer and this layer, which has got this sort of a structure. You can see where I'm pointing. This is this layer which is marked by B1, this layer. But there is also a flow of air, which is a second fluid, and that flows through this layer as well as this layer and this layer, right? This second fluid, which is air in this example, that also flows through these channels. So these are channels and these are actually fins. These are fins. So this example is a little different from the previous example that we saw. That was a finned tube heat exchanger. There we had a liquid and a gas, right? The liquid was that wastewater and the gas was air, which we were heating from 5 degree to 30 degree in that example. But in this case, this is a gas-to-gas heat exchanger. So many plate fin heat exchangers are gas-to-gas heat exchangers. You can use liquid also in some applications, but more dominantly, they're like gas-to-gas heat exchangers. And gases give you low heat transfer coefficient. We had a discussion on that quite some time back. So they need fins. And since both are gases, both require fins in the surface. Right? So that's one thing. It makes the geometry more complicated. So we will need to have a careful look at this geometry to be able to define both the areas. See, we need an area A1, we need an area A2. Ultimately, it will still come to that UA calculation. Right? So this is one observation. The other observation is that if you look at the top layer carefully, you will see that what I had drawn, this seems to imply that the way I had drawn, no? The way I had drawn, it was like this, like ribs on a surface. But it's not actually continuous. So you are breaking this one and shifting this second layer. So in your mind, imagine moving this one, this side, and aligning all layers. Then it becomes like this. Correct? But what is done is we don't use it like this. So we have only up to some length. And then behind this, we have another layer which is offset. So the word is offset. Okay. So this sort of arrangement is a plate fin heat exchanger employing offset strip fin. Offset strip fin. This is what it is called. And plate fin heat exchanger can have various kinds of geometries. And they can have triangular fins, rectangular fins, wavy fins, and offset strip fin, which I have just now shown you. Right? Now here are some photos. Okay. So this I've taken from some other book. I will have to tell you the name of the book later because I don't seem to remember which book I took it from, but originally it is from some manufacturing company. It's called Delphi Harrison Thermal Systems. This is in New York. Okay, so these are various arrangements. So this is a plain triangular fin. This is plain rectangular fin. This is like a continuous thing, which this is similar to what I had drawn a few minutes back. Okay. This is wavy fin. This is the offset strip fin that I'm talking about. Okay, so you can see that offset. This is a photograph. This is not a sketch, right? And then we have multi-louver fin, which is at E, and we also have some perforated fins. So obviously we cannot describe and understand all geometries and do calculations for all kinds of geometries. That you will do if you work, if you get a job in this area and if you design heat exchangers. But we will primarily focus on this OSF, offset strip fin. And this is kind of an exploded view. This I got from, this is a screenshot from a video which is available on YouTube. And this is plate fin heat exchanger. This is from engineeringlearn.com. Okay, so this is how it looks like. So this is kind of like we've separated. This is a sketch in which you've separated the plates and the fins uh, so that you can see a little better. So these fins can be brazed to a plate, or there can be some other manufacturing method of putting them together. And in this case, this shape is not exactly like this. This is a wavy fin, right? So that's this one. Below also it's something like this. And you see this two fluids are in cross flow, right? One fluid going this way, the other fluid going this way. This flow and this flow. One fluid going through one layer, the other fluid going just below this in the other layer in the other direction, 90 degrees, right? Okay. This is a cross section. Short video. This is how this is put together. This is, you can say this is an assembly thing. All right, another view. This is taken from another book. So you can see these fins a little better in this view. So you can see that the fluid, so let's say there's a fluid going like this. The fluid will have to face obstructions. The fluid cannot, I mean, if this was an extension like ribs, then the fluid would have just passed through these, right? Straight. But here you're always disturbing the flow. So that's better usually, right? When it comes to heat transfer, this sort of disruptions, these are better. Just physically, without doing any equations, these are better. Why? Because you make the flow more turbulent and there will be better mixing. So the transport processes will be more effective and you get better heat transfer. Right. So this is, if you follow this arrow, this surface is a fin height area and the fluid actually is in touch with that surface, isn't it? So that's why it's shaded like this. Okay. Okay, just let's focus on this figure. This is the figure that we started with. Let's focus on this figure once more. The number of passages for the hot fluid and the number of passages for the cold fluid are different. In this figure, hot fluid is fluid 1. Okay. What flows in the top layer from this figure? Top layer. Now you have this box. So top layer, what is flowing? Air, which is a cold fluid, right? Top layer is a cold fluid, and the bottommost layer will be a cold fluid, right? And in between, you have these hot fluid passages. So the number of passages for the hot fluid and the number of passages for the cold fluid, they will not be the same. Correct? What is the purpose? Why do we flow the cold fluid at the boundary? Yes, if you use a hot fluid at the top layer, then what happens is that it will lose heat to the surroundings. Then you are losing heat. No, the whole business of this heat exchange process, what we are trying to do is trying to capture that heat and use it for our own purpose, right? So maybe we're trying to heat the air using some flue gases. There's some combustion taking place somewhere. So we have this gas fluid one, which is hot fluid. This is, let's say it's flue gases, combustion products. Then you flow air and then you use the heat contained in that hot exhaust gas to heat the air, which maybe you will use it for some purpose. Right. So this is the idea. So these passages are not the numbers are not the same. Okay, so this is geometry. Then the most formidable task that we will have will be to describe the geometry. For that, we just don't have enough time today. Okay, but I'll introduce the problem of defining geometry today, and then we'll go to it on Friday. So OSF, offset strip fin, that sort of plate fin heat exchanger is actually quite popular, and it's compact. It gives you substantial heat transfer enhancement because we're using so many fins, right? So that will give you, that will increase heat transfer, and that will give you a high value of that beta because you're increasing area significantly. And the other thing is that, as I mentioned, the fluid goes through this, right? So it will, this is the starting, this is the face of the heat exchanger. So you will have boundary layer developing. Okay, nobody will argue with that, I'm sure. The boundary layer will start developing here, right? This side boundary layer. But the boundary layer will get disrupted because it will only develop up to this place, and then it, because of the offset, then again it faces an obstruction. Then there will be disruption of the boundary layer. So the disruption of the boundary layer so that will give you better heat transfer. So substantial heat transfer enhancement obtained as a result of periodic starting and development of laminar boundary layers. Periodic, because you do this, then you do disruption, and in the disrupted, I mean, then that offset pin section, again there will be another development of boundary layer. Then again it gets interrupted like that. So this will be better than the case when you are not interrupting it. But as you know, I hope you have understood by now, that if you get higher heat transfer, it will be accompanied by higher pressure drop also. Because if you have so many obstructions and disturbing the flow and all that, you will get higher pressure drop along with the high heat transfer that you get. And our channels will look like this, or maybe we can just go to this. So this is just